right, so continuing with inverse functions, we're now going to let f of x equal the tangent of x. And so then f inverse of x is going to be what I refer to as the arctangent. And I want to talk about why that's the arctangent in a second. The tangent only has an inverse function if we restrict the domain from pi over 2, or negative pi over 2, excuse me, to pi over 2. So it's a lot like the domain of the sine to get an inverse function. Reminder of where the tangent comes from. So let's consider part of the unit circle, that first quadrant of the unit circle here. And I have some ray coming out there at an angle of theta. And then from this point, we have an x value, and we have a y value, and the y value is the height of this triangle at that perpendicular line right there. If this is a unit circle, then that's 1, this length is 1, and that's 1 right over there too. And on here, the tangent of theta is equal to opposite over adjacent, so I get y over x there. And on the unit circle, that angle right there is also the arc length. So this angle we're measuring is also the measure of the arc length if I have radius 1. So the tangent given an arc length on the unit circle produces this quotient over here. Now we're reversing that here, and maybe I should throw some thetas in here instead. So let's switch variables. Instead of x, we're going to use theta. So here, if I say y is equal to the tangent of theta, then technically the inverse is that theta is equal to the arctan of whatever y I give it. Now this y is not the same y as the unit circle, unfortunately. It's a different universe, kind of. But theta is an angle. On the unit circle, an angle is an arc, which is why this is called the arctangent. Sometimes it's abbreviated as tan inverse, but that is hard to type in a lot of calculators. Some calculators have a button for that and others don't. So I can't remember what Desmos and GeoGebra have for that, but I think, let's get rid of some of this stuff. In most modern calculators that are on a computer, I can just type something like y equals the arctan of x, and it will give me the correct function there. Let's see, what do they have on their keyboard? Functions. And here they call it tan inverse here. And tan h, don't worry about that. That's a hyperbolic tangent. I'm not sure if we'll get to those this quarter, but maybe. I usually like to get to those. So you probably haven't seen hyperbolic trig functions. Has anyone seen hyperbolic trig functions? Does that sound familiar? Nope, nope. So, okay, we'll have to look at hyperbolic trig functions this quarter. Sometimes it's covered in pre-calculus, sometimes they're not. Why do we care about hyperbolic trig functions? Sorry, this is a tangent. Bad math joke. Hyperbolic trig functions describe many things in reality. In particular here, if this is a telephone pole over there and there's another telephone pole over there, and we try to string a cable in between them, no matter how tight we pull the cable, gravity's pulling down on it, so it's going to make this U-type shape. So that cable arc here is a hyperbolic trig function. Hyperbolic, which one is that one? I think it's the hyperbolic cosine. I gotta look that up. And the shape of that arc there is called a catenary, which I may or may not have spelled right. So they're kind of worth studying for that. For sure, they end up being covered in Calc 2, and I'll have to look to see if they're in this book. Can't remember off the top of my head. All right, so that was a side note. Let's get back to this problem here. So anyway, I prefer the notation arctangent to tan inverse. And so you see me write arctangent more often than anything else. So anyway, what I want to do is I want to find the derivative of the arctangent. So let's see if we can do that. So we know that f prime of theta, derivative of tangent, is the secant squared. And the inverse function theorem says if you want to take the derivative, in this case with respect to theta, of an inverse function, in particular in this case, I want the derivative with respect to theta of the arctan, which is the inverse of the tangent. It says take 1 over the derivative of the inverse function. So that would be the secant squared, and then evaluate it at the inverse function. So that means inside here, I have to plug in the arctan of theta. Interesting. I'm just going to clean that up a little bit. New page. Actually, I kind of want to stay on this page for a minute. We'll make it work. I'll rewrite it right here. I'm going to write it as 1 over the secant of the arctangent of theta. And then I'm just going to square the whole thing. Sorry, I'm running out of room there on the side. So now I got to figure out what is the secant of the arctan. Well, back here, the arctangent is an angle. Okay. So if I look at this picture up here, the tangent of theta in this picture is y over x. What I want to know next is what is the secant of theta. So in this picture up here, let's switch to blue, what is the secant of theta? And actually, I don't want to use that picture. I do need a new screen. So let's go, we want to figure out what is the secant of the arctangent of theta is what we're trying to figure out. And to do that, I got to go back to what the arctangent means. So if y equals the tangent of theta, then theta equals the arctangent of y. Sure. And then in my picture here, actually I just need a triangle. In my picture here, I just need to evaluate what that means in my picture. So tangent of some angle, so here's my angle. And tangent is opposite over adjacent, right? So that means I have to view this y as y over 1. So my opposite side is going to be y, and my adjacent side is 1. The Pythagorean theorem says that the other side then has to be the square root of y squared plus 1. And then as far as the secant goes, the secant of theta in this picture, secant is 1 over cosine. Cosine is always adjacent over hypotenuse, so secant is hypotenuse over adjacent. So in this picture here, the secant is going to be the square root of y squared plus 1 over 1, or just the square root of y squared plus 1. Remember doing that, evaluating trig functions of inverse trig functions. Hopefully that rings a bell back in your trigonometry days. So what I know up here now is that the secant of the arctangent of theta is equal to the square root of y squared plus 1. And since we're doing functions of x, I probably should have called that x. So we're going to call it the square root of x squared plus 1, because both the function and the inverse are functions of x. So I really need an x there. So back here, let's see, I'll just go to another page. So here's where we're at. We've got the derivative with respect to x of the arc tangent of x is equal to 1 over the derivative of the tangent, which is secant squared, and then evaluated at the inverse function. Forget about the square for a second. We know that the secant of the arctangent is the square root of x squared plus 1, and we're also squaring that. So now I get 1 over x squared plus 1 should be the derivative of the arctangent. So let's see if that really works. Is this really the slope function? We can check that on our graph by just picking some points. So I've got, let's rewrite that as f. We'll call that g of x equals the arctangent. And I think the slope function, I like to call d of x for derivative, is equal to 1 over x squared plus 1. And I really don't need to see it, so I'm going to turn it off. But what I want to do is see if I do have a tangent line. So let's just pick a point like 2 comma g of 2, so that point on the graph. And then the tangent line at that point should be y minus g of 2, y minus y1 equals the slope, which is the derivative, plug in 2, times x minus 2, and that looks like a pretty good tangent line right there. So we're going to do that again with another function, and then you get to practice this for homework. So we might as well stick on the subject of trig functions and try this for another trig function. Let's try the sine. So we'll let f of x equal the sine of x. In order for f to have an inverse function, then we have to restrict its domain, and it turns out the common restriction is pi over negative pi over 2 to pi over 2. And the inverse, I prefer to call arcsine, but it's also equal to the sine inverse of x. And I want to know what is the derivative with respect to x of this arc function, this inverse sine function. And the theorem says that we take 1 over the derivative of the original function. Derivative of sine is cosine. But we evaluate that cosine at the inverse. So then we plug in the arc sine of x. So now we want to figure out, well, what is the cosine of the arc sine of x? So that's where we do a little right angle trigonometry. And to do that, we remind ourselves that theta is equal to the arc sine of x, right? Arc sine is an angle, which means the sine of theta is equal to x. So on my picture here, this is theta. Sine is opposite over hypotenuse, so I'm going to view that as x over 1. So then I call this side x and I call that side 1, because sine is opposite over hypotenuse. If we use the Pythagorean theorem here, we're going to get 1 squared minus x squared inside of a square root. 1 squared is just 1. So then this side has to be the square root of 1 minus x squared from the Pythagorean theorem. Okay, so the reason I need that is the cosine of the arc sine of x is an angle. So in other words, in this picture, what is the cosine of theta? And just a reminder, the arc sine of x is theta. So in this picture up here, what is the cosine of theta? Well, cosine is adjacent over hypotenuse, so it must be the square root of 1 minus x squared over 1. No point in dividing by 1. Right? Cosine is adjacent over hypotenuse. So that means my denominator here is really the square root of 1 minus x squared. So I now know that the derivative with respect to x of the arcsine is 1 over the square root of 1 minus x squared. So again, we're collecting a bunch of derivatives we need to remember for the most part, although we can look them up when we need to. Just like I hoped you know that the derivative of the sine is the cosine, now we know that the derivative of the arcsine is 1 over the square root of 1 minus x squared. And we could easily test that by just plugging in a number on the graph. So let's clear this out, give that a quick test. So I'm starting with f of x equals the sine of x. G of x is the inverse, which I'm going to call the arcsine, which you could also pull out of the menu functions and then inverse sine. That'll give exactly the same graph. And again, remember we had to, in order to get an inverse function, we had to restrict the domain. Otherwise, if we try to do something like, say, instead of y equals sine of x, x equals sine of y, you get this wave vertical that's not a function because it fails the vertical line test everywhere. We had to have a domain restriction. Don't need to see this one, but I do want to see g of x. We think the derivative is 1 over the square root of 1 minus x squared. I don't really need to see the derivative, I just want to use it. I'm just going to zoom in a little here, and let's pick maybe, I don't know, 1/2. So I want to find through the point 1/2, let's choose 0.5. So there's the point on the graph. I want to see if this derivative function really is the right derivative function. Does it give me the right slope there? And so we can do a tangent line. Y minus y1 would be g of 5, and that's equal to the slope derivative evaluated at 0.5 times x minus 0.5. And if we zoom in there, that should look like a pretty good derivative, right? We're matching the slope of the black curve with the purple line at that point. So it looks like we got it. So the main reason we needed this inverse function formula is for arcsine, arccosine, arctangent, those arc trig functions. All right, so those were my big examples. A little less time than I thought they would, so let's do a surprise homework question.